This next module is probably going to open a few eyes. It's one of my favorites. It's called Sampling Theory and Practice. This was developed, as I mentioned earlier, in the mining industry because it's a very profit-driven industry, and there were, hard business cases that we could develop to show it was worth investing a little bit more in the sampling than it was having a bad year-end number on the bottom line for silver, gold, copper, even a coal corporation. And this same type of sampling technology rolls into basically any industry. And just kind of the hint up front is it all depends on two things. One, the concentration of what you're looking for. If you're looking for stuff in 5, 10, 20%, probably not so much. But if you're looking for trace elements, defined as things below 1 part per million or 10,000, 10,000 parts per million, or 1%. And most of the time we are in the environment, sometimes down even below 1 part per million, then it really applies. So trace elements. And the other aspect of it is geared toward particulate materials, soils, composting and amendments, silts, sediments, and so on, that have a lot of heterogeneity. And you'll hear that word a lot over the next few minutes here, is heterogeneity. Now, Tressa, should I start now with the questions that came up over the break?
Well, maybe you could ask us a couple of questions if the audience has them, and you can answer them as well.
Okay. Let me just throw out a couple things we heard during the break related to the data quality objectives. One, on the remote monitoring, it was mentioned that if you're not really in an enforcement situation, the extra data may not be necessary. They may be interesting, but they're not necessary. And I know we're doing projects where at their DOE sites they have like I won't mention the parameters, you can guess, but radionuclide plumes, okay? And they know it. They're below state levels, but they want to know if they're getting better or worse. They don't have to enforce anything. But one of these is thinking about putting in a permeable reactive barrier, all right? So we can measure water quality, measure water chemistry. That might be a business case, okay? But just knowing the interesting stuff, that might just be a PhD project, okay? So you kind of got to have the business case to go along with it. The second one was there was a lagoon mentioned that has uneven topography, that mounds and hills, so to speak, for various reasons arise, just the way this facility operates. And the regulated party needs to estimate the volume. And they take a certain amount of data, which may or may not be sufficient, and they say it'll be X number of tons. And they come to the regulator and they say, well, we don't think it'll handle that, or that's too low. And so then they all get in, this kind of situation. This is a great example of why the DQO process should be used up front. A phone call or an hour meeting might solve that. Before people go out, spend the money, come in, find out the regulator doesn't like it, and then you get all into the headbutting contest. Okay, these global issues may be able to be solved up front. Okay, I also had, as I mentioned, a few statistical kind of tricks I can pull out of my bag. They may help either party. I don't know. I can never predict whether it's going to be good for the regulator, good for the regulated party, whether it will save money, cost more money, but it will apply the objectivity in the decision making that we talked about. Okay, so kind of ruminate on that. This particular module is, I hope, going to open your eyes a little bit. And it's a little scary, but there's good news here is that we know a lot of the reasons we have these sampling problems and how to mitigate, to the extent possible, the errors that are involved. And actually, it can cost more money, but a lot of times it doesn't cost any more money. In fact, one of the success stories at Savannah River, and we'll see in the case study, is that we saved them at least $30 million just by kind of rearranging the way they went about sampling. And it saved them millions. Okay, so as I said, I can never predict, but if you don't do it, you tend to get in these cross headbutting situations. Okay, so the sampling theory, this originated, as mentioned, in the mining industry. Miners are out there exploring for precious metals of various types. It's a risky business for a lot of reasons. And one of those reasons is they have extreme heterogeneity in the materials, i.e. the rock, that they're sampling. Now, there's a lot of types of, say, gold properties. You can have vein gold, where it goes along the cracks and crevices, and you have sometimes sheets or nuggets or, big pockets, sometimes very thin or very narrow, that you maybe mine with a underground situation, or maybe you come in from a surface mine and do that. But anyway, if you drill down and they use like 1 inch, 2 inch, rarely 3 inch core, you might miss it, or you might get the nugget. Okay, so how do you deal with that? And if you get the nugget, and gold is really insidious, because if you happen to get a little nugget in that volume and you put it in a little puck mill and you grind it into flour, guess what happens? I remember seeing a Mr. Science deal where they took a Krugerrand and they rolled it out into this big sheet about the size of that sign back there, and the guy could stand in front of the sheet of gold. It was so thin he could see right through it. Okay, same thing happens in the puck mill. The host rock dissolves and becomes powder. Okay, the gold, it just flattens out. So when you go in and you take that, say, a 1 gram sample and put it into the AA, the analysis, the flame